connecting from. They could even know what street you're on. And if they don't like what you're saying or what you're doing, they might come and stop you. Or they might take your server offline. Or do any number of things to prevent you from communicating with who you would like to. What we want to get to in this future of a more secure internet is a way that addresses don't automatically match to the physical location that someone is on the globe. So as you can see here, we have what we call a peer-to-peer overlay. And this peer-to-peer overlay prevents you from knowing where someone is in the world when they connect over this network. Another important thing that we need when we use the internet is that humans are not very good at memorizing long numbers, right? We don't even remember our own phone numbers anymore. We just program them into our address book and then promptly forget them, right? So we have to use words. We have to use names, memorable names, to connect the places we want to go with the addresses where they're located on the internet. So that's why domain name services were invented. This is called DNS. Has anyone heard of DNS before? DNS is how you get a website. When you want to build a website of your own, you go and register a domain name, right? And who gets the domain names is controlled by a central authority called ICANN. And if they don't like the particular name you want, or don't want to let you have access to this domain name, they can prevent that from happening. Or if there's some organization or authority that doesn't like the content you're producing, or for some reason has something against you, they can use various means to take your website down through altering domain name services. Another thing that could happen is you could be at an organization that's providing domain name services but is not including the entire database of names when you look them up so that they can be found, or is actively preventing you from looking them up. So there are things like the Great Firewall of China or other things like that that prevent people from accessing all the information that they would like to. So what we're trying to move to in what we call Web3 technology, the next web that's being built, is a service that is managed in a decentralized way. And one example of that service would be Ethereum name service. And it uses a blockchain to keep track of who's registered which domain. And there are several others as well. Another important feature that we're missing in today's internet is good authentication systems. So how many of you have passwords that you use to access your favorite websites? Right? Everybody should be raising their hands. How many passwords do you have? Do you have more than 100 passwords? I do. I have hundreds of passwords. I have thousands of passwords, and I use software to help me remember all of my passwords, right? And but most people don't do that. Most people just have like one password for every site that they visit, right? And that's very, very insecure. That's very unsafe. If anyone found out your password, they could access all of your information. And in some cases, passwords are getting leaked or lost, or someone's hacking into a place that stores your password, and then they use that same password and access all of your other information. So we've got a password problem. Identity in this future web that we're building needs to be what's called self-sovereign identity. With self-sovereign identity, the owner of this information is in control of it. They decide when their information gets shared, and they make sure that only a small amount of information gets shared. And if they ever want an organization no longer to have access to that information, they can also revoke those privileges. Another important thing that's being reformed and improved by this new web is payments. So this is the most famous case for blockchain, right? Blockchain has already revolutionized the payments industry. We can now transfer value across country boundaries in short time. And all of these payment solutions that we used to use are being disrupted by this new technology. One important other feature of this new web is higher resistance to surveillance and censorship. So we already use encryption wherever we do secure things online. When we buy something, the lock in your browser tells you that it's encrypted. But one thing that we're not doing well enough yet is that just encrypting the information might still allow you to know that some individuals are communicating with each other. And knowing that some individuals are communicating with each other, even if you don't know what they're saying, could leak information in dangerous ways. So we need to have information and communication systems that don't allow this. Also, someone might maybe they don't know what you're talking about, but they might want to prevent you from communicating with someone else. They could block the channels that are between you and the people you want to talk with. So this is called censorship, when they block the communication, and surveillance, when they spy on who's talking to who, right? And one of the things we're working on is a communications protocol, which is displayed here in this conceptual diagram. In this diagram, the person at this node, AC, is trying to communicate with the person at node BC. And one of the techniques we can use to make that more resistant to surveillance is what we call partial addressing, or dark routing. So in this case, we have a message that's prepared for BC, but instead of saying that it's destined for BC, we just say that it's destined for B blank. So B, anything that starts with B will be sent this packet. So you can see that the packet gets routed efficiently along the path until it matches every node that begins with B. And then once it gets there, it gets sent to everyone whose address matches. And within this zone that the address matches, it's very difficult for anyone who's monitoring that traffic to say where the traffic originated from or where it's destined to. And so within that zone of darkness, you essentially gain resistance to censorship and surveillance. And we will provide tools to our users to help them to determine how much of the address they should specify when they're sending packets to each other. Another important feature is the ability to store files. So right now, when you store files on the internet, you store them on a specific server or group of servers that's managed by a company or an organization. But that focuses too much power on one central group, right? So what we want to do instead is provide storage through a peer-to-peer network where no one is in control and everyone is in control. So it's a network where anyone can participate in this network. It's peer-to-peer, and this file that you're saving to the network will get broken down into small pieces and distributed across the network. And each participant in this network is storing some of that file in an encrypted format. And people have to pay when they want to download the file chunks, and they get paid if they're hosting those file chunks. So it's an economy that ensures that that storage solution will stay online. And we'll talk more about that. Another thing we need to do is be able to look things up quickly. So we don't just want to store large static files. We want to store data that can be accessed quickly and queried for specific information. And that's why we use databases. But these databases right now are stored on one server somewhere or a cluster of servers that's managed by people. We need to instead migrate to a pattern where this stuff is distributed all across the world on several nodes in our peer-to-peer network. Another important thing that we need to be able to provide for applications to be truly decentralized is computation. So the ability to crunch data, to figure things out, even when your phone or your laptop is not connected to the internet. So right now, you're relying on servers to do that for you. But these servers are single points of failure that are managed by companies and organizations. And we're trying to move to a model where these services are provided by a peer-to-peer network. So in this network, you may have a computation job that you need executed, or the application that you're running, you need to do this. So it will actually look for a computer that is willing to do computation, and it will send the task over and send the data privately, have the computer do that task, and then send it back to you. And that way the computation can happen. So in our, as you can see as I've gone through this, I'm going to do the, I don't know, I guess I don't have the laser pointer. Anyway, all the stuff on the left-hand side are solutions that are currently being used to do these things. And we're moving to a new paradigm. And now I'm going to turn the time over to Brad to talk a little bit about incentivization.
Thanks, Carl. All right, so none of this honestly works without incentivization. Mainframe actually has been around for a couple of years, and we've been working on a lot of different things. And one of the things that we realized very recently in the last couple of years was without incentivizing a network of nodes to perform different tasks, it doesn't work. Nothing works, right? And there's a quote here that says, basically, you can get people to do stuff by rewarding them. Carl talked about file storage. We talked about dark routing, relaying the message across the different nodes to different people. What we're doing with Mainframe is we're incentivizing these nodes to relay data packets or to store data packets. And this is a really important thing. And we want to test this theory out a little bit. Kelly, why don't you come up here and help me out? But we want to see if we can get some of you guys to do something if we give you a reward. Can I get a couple of volunteers? Who wants to get a reward for doing something? All right, we got one volunteer. Come on up. You want? Okay, come on up.
It's a fun game.
It's a fun game. It's a fun game.
No,
the winners are going to get extra Mainframe tokens. All right, here we go. We got 3. We need one more. One more volunteer. All right.
Yeah, come on.
All right. Come on up here. All right. So wait. Oh no. Hold on. I think I picked him. Hold on. Where did you come from?
We have 4.
No, but she was 1.
Oh, you were 1?
Okay. Hold on.
Paper,
Yeah.
rock, scissors.
Okay, I don't think I chose you. I'm sorry. I'm very sorry.
Take this one over.
Okay. So here's